Fun. Now, got it. Got it. Fun. Fun. Okay. Well, we will start if it's okay with you. There is a second question. So, dear professor, can we know the topic of today? Yes, it will be the tensor formalism. And oh, thank you, Shao. So let's start with today's course and. Well, lovely. So far, we look into a different coordinate system, and indeed, we talked about the curvilinear coordinates and in general the coordinates which we have. In general, they can be given by in n-dimensional space, and in the n-dimensional space, we consider those that they have the unit vectors of the parameters. They are orthogonal to each other, and then we got the way that we could express the vectors. We could express the infinitesimal displacement of dr in that coordinate, the elements on the surface, the element of volume, which in some cases it was linked to Jacobian. And also we calculated what's going on with different integrals. I mean, if you take a vector, which is a dr in that specific space, and then you look into do the calculation of either v dot dr or v dot d sigma, or the vector multiplied by the volume and doing the integration. And then in one specific case, we proved that the divergence will be given by the parameters of the space, which was h1, h2, h3, and they were linked to the diagonal terms of the metric in that space. And then I say that in the similar fashion, you can prove what's going on with the divergence and what is going on with the curve. And we did the calculation for one specific coordinate, which was a cylindrical coordinate. Or I have to be a little bit careful and also be precise, circular cylindrical coordinate, because there were another example that I mentioned that it can be elliptical cylindrical coordinate, or you can go with spherical coordinate, which will be given in assignments soon, or maybe today, or at most by tomorrow. So far, we know how to work with the curvilinear space, but slowly we have to go with more general formalism, because students, they ask why we care about writing in a cylindrical coordinate. We can write everything in the Cartesian coordinate. Is very easy to handle, because in that specific coordinate, the Cartesian indeed x1, x2, and x3, which they were unit vectors, they were constant. I mean, they were not function of the coordinate, is identical everywhere in the space. While if we work with the q1, q2, and q3, we have to be very careful, because these q's in general, qi, they are function of other parameters. It can be function of q1, q2, and q3, and then we have a tough time of calculating let's say, integrals or derivatives, because those are the coordinate dependent. So I say that, well, it all depends on the symmetry that you have. Not always we have Cartesian symmetry, but in some cases we have cylindrical symmetry. In some cases we have spherical symmetry, or elliptical cylindrical symmetry, or even hyperbolic symmetry. So it all depends on the physical problem that you are tackling. And I gave an example when I was a master student, how tough time I had doing the calculation of finding magnetic field for two solenoids. Well, okay, so far so good. And I will give you some examples, I mean, later on in the assignments, that you can look into physics problem, which can be simplified in one of the coordinates, and it's tough in the Cartesian coordinate. Now I will go deep into the vector analysis, and I will prepare you for the some part of this is related to general relativity, and some of them they are related to manifolds or differential geometry, which is very important, and it shows up in many parts of physics, in solid state as well, and in optics as well. So let's go and look at the definition of the vector. So what was the definition of the vector? Assuming that of scalar and vector. Well, we say that you have a coordinate. You take this coordinate of, let's say, x1, x2, and x3, and you rotate it. For example, I can rotate it around x3, and you create a new coordinate of x prime 1, x prime 2. And maybe if it's along x3, then x prime 3 will be the same. If you do an arbitrary rotation, for example, that can be even like that. So it can be like these, and these. So it will be x prime 1, x prime 2, or x prime 3. You can do any rotation of the coordinate. So if you have a scalar quantity here, like a temperature, this scalar quantity of temperature, then upon this rotation is not changing at all. So the scalar quantity T of x prime 1, x prime 2, and x prime 3 is the same as T of x1, x2, and x3. Okay, that's it, was the definition of the scalar quantity, which upon the rotation, nothing has changed. However, for a vector quantity, let's say vector of A, then what we know that A, of course, in the x coordinate can be expanded at A1 x1 hat plus A2 x2 hat plus A3 x3 hat, which is again is the same vector as A prime, which is A prime 1 x prime 1 A prime 2 x prime 2 plus A prime 3 x prime 3. Okay, so we knew that's the same vector. However, since x prime 1, x prime 2, and x prime 3, they are rotated now, they are the different unit vectors, then correspondingly this term A prime 1, A prime 2, and A prime 3, the components also now they are changed. How they change in the space easily, I mean, talking about that, we had the formula that A prime I is given by Aij Aj summation over the J. Okay? And what was Aij? Aij was the derivative of x prime I with respect to xj. We proved this in the past. And someone, if you want to know that, if you assume this relation, the one that we have it, if you multiply both sides by x prime I, then what you will get that aij is equal to x prime I dot xj. Okay, that was also what we obtained from the definition of the vector. And one of the examples of these was R, right? So we had R, which was x1, y x2 plus z x3. And we showed that also R is changing in this fashion. And we had also similar the expression, but for not for this kind of vector, but we had it for the gradient. If you remember, we did a calculation of d phi of x, y, and z, and we say that if we change the coordinate, that will be also the d of phi prime of x prime, y prime, and z prime, which we express in terms of x1, x2, and x3, and that was x prime 1, x prime 2, and x prime 3. And then from here, we obtain the gradient, the definition of the gradient of phi. And we say that if you look at the elements, the i's component of this gradient, which is indeed is the derivative of phi with respect to xi, then we can look at this component, how it's changing from the two coordinates. And we obtained that derivative of x prime I of phi is given by summation of aij derivative of phi with respect to derivative of xj. Okay, and that was the summation over jj. J was 1 from 1 to 3. And what we realize here, aij was the derivative of xj with derivative of x prime I. So if we use the chain rules, if you remember, we want to calculate the derivative of phi with respect to x prime I, and we say that this phi is now is a function of xj, and which means that is x1, x2, and x3, and then we use the chain rule, and we had the derivative of xj with respect to xi, but now we have to summation on all of those x, and then we have the derivative of phi with respect to xj, and we call these, and there is a prime number here, the prime index here, so it will be aij. Well, look at these two aij's. One of them, aij, is given by derivative of x prime I with respect to xj, while for the gradient, aij is given by the inverse. So it's given by the derivative of xj with respect to x prime I. Okay? Do you have a question? Okay, so no question. So these it brings me to a conclusion. So note that in Cartesian coordinates, these two aij's, they are the same. Aij from the first one, which is the derivative of x prime I, derivative of xj, is identical to the derivative of xj, derivative of x prime I. But in general, these may not be true. So if you have some, for example, you will see in maybe by the end of this lecture that in cylindrical coordinate that might not be true, or any other arbitrary coordinate that I have. So then Well, I have to distinguish these two vectors, the vectors that they are changing like that, and the vectors that they are changing like this. What does it mean? That they might be a vector which A prime I is changing like the summation of derivative of x prime I, xj, aj, or I may have another vector, which I call it, let's say, v, which v prime I is changing like summation of xj, x prime I, sorry, just to make it the same, vj, and that's a summation on j. Okay, so there might be two kind of vectors now. One of them, the aij, is given by this term. The other one, aij, is given by the inverse, which is a derivative of xj with respect to x prime I. As I say, in the Cartesian coordinate, we don't have this kind of problem. So I distinguish these two vectors. I tell that these in general, they are different. And I call the first one contravariant vectors. And this one, I call it covariant vectors. Okay. So, well, in order to distinguish these two, because not always they are written in this way, the covariant vectors, which they act like R, remember that was the formalism that R changes. So R changes like R prime I, which if you look at the component of that, they had aij, which is given by derivative of x prime I with respect to xj. And this one was looked like the gradient. So it was the gradient of xj or xi prime, which aij was derivative of xj with respect to x prime I. Okay. So in order to distinguish these two kind of vectors, I go with superscript index, and I will go with the other one with a subscript index. They are vectors, remember that, okay? So still they are vectors, but I will distinguish them. So here after any covariant and any contravariant vectors, I will label them differently. The contravariant, I will label them with superscript index, which is AI, while any contravariant, I will label them with AI, okay? Or it can be a different vector, VI or BI. Here it can be BI or BI. Okay, is the convention that I will use to distinguish them, that they are acting differently. One of them is look like the coordinate, the other one is more look like the gradient, which is they are changing in space, okay, or upon rotation. No, they have absolutely no relationship with clockwise or counterclockwise, not at all, okay? is a name that I'm associating to them. One of them is changing like R, the other one is changing like the gradient. Okay, these two are different, and the only difference, remember, the only difference is coming back to this one. Okay. Hereafter, I have to be very careful where I put the index, on the superscript or on the subscript. Okay, these two, they are different because they will tell me which form of the vectors they are. Okay, let me see if there is any coordinate. Hi, are these coordinates parity differentiable with respect to each other? In experiments that we are easily using them? Well, it can, you can partially differentiable. Yes, of course. I mean, is what I'm doing. Any other questions? Because it's very important to understand the concept now.
One has asked, is that vector is covariant transformation vector?
Is that vector covariant transformation vector? I'm not understanding the question properly because this is a vector which I call it a covariant vector, okay, which is changing like this rule, and that one is a contravariant vector which is changing based on this rule. Transformation vectors, yes, they are based on the rotations, as I say. Is based, I'm looking at the coordinates, how the coordinate is rotated, okay, and then I look at the vectors, that how they respond to, I mean, the components, they will be describing based on these rotation. And I'm not rotating the vectors, I'm rotating the coordinates.
One has asked, A sub ij are same for Cartesian coordinates. I want to know how to show it by explicit calculation. Are covariant and contravariant vectors same in Cartesian coordinates?
Yes, this is I have shown. If you look at the previous lectures of the, I think it was the second lecture or the first lecture, which I showed to you that, guys, when you take the gradient and doing the calculation, you will find out that Aij is the same, is exactly the same one. And from these, I found the delta Kronecker. Okay. If you never mind, please go and look at that video. If you cannot find it, then just drop me an email. So now let's.
No more questions, sir.
Okay, fantastic. Thank you very much, Vision. So now let's look at the contravariant and the covariant formalism and see how can I write them. So remember, always superscript is for contravariant. Subscript is for the covariant. You cannot mix them up, okay? It's very important to pay attention to that. So now, based on this knowledge, how the transformation will happen. So AI prime, of course, in the rotated coordinate, the component of the vector now is given by the summation of Aij, and then I have Aj. So a contravariant vector is linked to the contravariant vectors of the not rotated coordinate by these Aij. What is this Aij? Remember, in the contravariant formalism is given by derivative of x prime I, derivative with respect to xj. Okay. Now I pay attention also to put the superscript or subscript for the coordinates as well. Okay. What is happening with, that was a contravariant. What is happening with the covariant form? So A prime I, now look, I'm using a different notation, which is instead of superscript is a subscript of a I j a j. In your book, they have not written in this way because, well, I prefer to write it explicitly like this because it's way easier for me. And pay attention again, a quariant vector is linked to a quariant vector in a non-rotated coordinate. But what is this value? Aij is the derivative of xj, derivative of x prime I. Okay? For simplicity, some people, they write it in this way. Derivative of j of x prime I. This one, in short, they write it derivative prime of I of xj. So the entire of this, since it's a derivative with respect to x prime, you write it as a prime, but with respect to which index, which is with respect to I index. Is a superscript, it becomes subscript. It seems that the derivative is bringing it down. If it's down, it brings it to up. And that one also the same fashion. Write it as a derivative with respect to j. Okay? So that's the first thing. Any questions so far?
No questions so far.
Okay, lovely. Remember, those are the conventions that I am using, which is a standard convention that people, they use it in physics. And but is the contravariant, which is superscript, covariant is subscript, okay? And the vectors are given in this way. Now I have another convention that you have to learn, which I call it Einstein convention. So it is very difficult always to carry the summation. So we don't like to carry the summation with ourselves. What we will do? Exactly, we will drop it. So we will take away the summation of j, but we should know which index or indices are summed over. Okay? For example, if I have a look at the first one, a prime I is given by summation on j aij aj. We will omit the sum. We take it away. So this summation, I will not write it down, but I will write aij aj. Now the question is that which one of those indices I'm taking the summation over, the one that is repeated. Okay, so that's the convention that we now learn. So in order to write quickly, we will omit the summation, but we remember that the indices that they are repeated, I have to take the summation. Now, if I write aij, AJ, this means that I have to take the summation over the J. The same way for the other one, I can write A prime I, which is the summation on J of AIJ, AJ. So using the summation convention of Einstein, I will go with AIJ, AJ. Means that I will do the summation over the J. Okay. So can you tell me what is this? I'm writing an example, okay? I will write A, I, J, K, L, B, K, C, L. Can you tell me what is the result of this? I will look at the Q&A. Yes, Mohammed, you are right. So we are doing the summation over the repeated index, which is a dummy indices, which is that one. So I B C, okay. To okay Vij. So Shaho says that is Vij. AIJ on KL. Okay, exactly. So the two indices that they are repeated is the K and also L. So whatever is the result, I will call it F, now is independent of K and independent of L. So I will call it IJ. Do you agree? Exactly, or AIJ is up to you. Yes. Or any IJ. Good?
Yes, there are a few questions.
Yes, please go ahead.
Amir Hussein has asked, earlier you mentioned we can say that AIJ are acting like dot product, so there must be an exchange relation between them. Then why is it different for co- and contravariant vectors?
Amir Hussein, it's the point is that it happens in the Cartesian coordinate, okay? In the Cartesian coordinate, you don't see these changes. But if you go to the cylindrical coordinate, you will see that those are different, okay? I will show at the end of the lecture, so how they are different.
Subramandal has asked, why for x in bracket, in the d by dx, you always use subscript. Is it possible to get subscript index in x in bracket?
Oh, you can write that. Yes, absolutely, absolutely. Yeah, but the point is that I have to start. You will see again towards the end of this lecture. You have to start with a specific space, which I call it the contravariant space of Qi, okay, or Xi. When you start with this, everything is easier to be built up, and then you build up the dual space, and then you extend the metric and etc.
Isa Muhammadi has asked, it's more like upper lower index cancels out lower upper index in the summation, right?
So it is more look like the upper lower index cancel out lower upper index in the sum. So yes, whenever the indices they are repeated, they cancel out each other. So for example, let me write this. Very good question, by the way. J, K, L, B, K, C, L. Okay. Now I'm telling you what is the what is the result of this. Of course, the summation is our repeated index, which is K, and it is repeated over L. So the result of these, it will be AIJ, lower, exactly. Isa. Lovely. So remember that that's the convention that I'm using it. Okay. No question?
No, there's no more questions.
In when you write in the Q&A, when you want to distinguish this one from that one, or in emails, just write it in this way, like a LaTeX notation. So a power of, let me write it in LaTeX formalism, a power of ij, okay? And that one will be a I J. This is the way that people they see it, and usually you put it between $sign, just to tell that these are mathematical equations. So if you write it, for example, I ask you some answer, you can write it as a power of ij, or a subindex subscript of yes, exactly, in LaTeX or TeX, yes, is exactly the same. Lovely. So now let's move on. Well, so far so good. We have absolutely not a problem, and I think we all understood that. Well, but now there is a difference is in the physical meaning of let's say vector R and also the gradient, and then we distinguish them in terms of the covariant formalism and the contravariant formalism. And well, we say that in the Cartesian coordinate, these two, they are the same. So that's a reason that we have not introduced them so far, but we will see later on that they are different in different coordinates. So well, scalar quantity, we say that it does not change, like the temperature, T is equal to T prime. The vector quantity is given by either of these form. AI prime is AIJ AJ, or there's a contravariant, or A prime I is given by AIJ AJ, which is the covariant formalism. What happens if I have something beyond this? For example, if we look at the pressure, do you believe that the pressure, the fluid pressure, for example, you have a swimming pool and you add water to it, and then you will see different pressures on different walls, okay, or different the bottom of the swimming pool. Do you believe that this pressure has a magnitude and has a direction? You can write it in the Q&A. Do you agree that it has a magnitude and volume? And direction? Lovely. It has only magnitude? No, it has direction, because the pressure will be that way, that way, that way, that way, that way. And like the stress, so I can take this notebook that I have here, I can take this notebook and I can twist it, okay? So, and you will see different tensions there. And this tension has a direction and also has a magnitude. Are they vectors? They are not vectors. They are something beyond the vector, which we call them tensors. No, they are, most of you got it in a proper way. How we can build up a tensor? And the tensor that we have here, well, indeed, the scalar and also the vectors, the two vectors that we define them, they are special cases of tensor. The tensors, indeed, are changing according to the vector calculus, but they have more than one index, okay? So they are, for example, I call it the tensor in the contravariant formalism, IJ, and this tensor is given by AIM, AJN, T m, and n. Remember, well, you can show it with the matrix representation, but it's not matrix. So matrix has a different definition. Matrix is unchangeable according to the to rotation of the coordinate. So one of the things that we previously introduced was GIJs. Do you remember the metric? The metric is a tensor. Epsilon ijk, that's another tensor that we work. Delta of ij, also that is a tensor, okay? But well, we will talk about those. Some of them, they are pseudo tensors, but we have to be careful with that. But remember, whenever you have more than one index to determine them, then you call them the tensors of rank of that indices. I mean, those are the repeated. For example, that is a tensor of rank 2. Okay, so if I can build up another one, which is a T prime I J K, which is going to be A I M A J N A K L, and then I have a T of M N L, so that's a rank 3 tensor. And all of those, remember, what are the indices? They are superscripts. So they are what we call it contravariant tensor. Okay. And again, remember, the summation is over repeated index, which is n and m for this one, is over n, L, and also m. Good. So in general, if I write these tensors, the first one, T prime ij, which is the contravariant tensor of rank 2 or second rank contravariant tensor, is given by summation of a I m a j n t m n, and this is a summation over m and n. That's the reason that I have written. So I'm expanding those calculations. So it will be the summation of m and n, derivative of x prime I, derivative respect to xm, derivative respect to x prime j, derivative respect to xn, tmn. So it seems that it's changing like the 2 cosine formula. Okay. So for example, momentum of inertia, which is I, that's also is a tensor. Refractive index is a tensor. Epsilon in materials, they are tensors. So you cannot handle them like a scalar. I mean, well, if your system or your material has symmetry, then it can be handled like a scalar, because the element of these matrices that you see, or the tensor that you see, they are diagonalized and you can factor it out. Okay, so that's a contravariant tensor that we introduce here. But you may have in a similar fashion. By the way, I can go with the third rank, which is exactly the same way. Third rank contravariant tensor of T prime I J K, which is the summation. I'm expanding this one, which is a summation of, I will explicitly write it down, x prime I, derivative with respect to x m, derivative with respect to x prime j, x n, derivative with respect to x prime k, that's a prime, derivative with respect to xl, and then I have a t M, N, and L. Okay. That is our M, N, and K. No, sorry, M and L. Okay. Mohammed, what you mean by TMN is different from TMN. The other one is, as I say, TMN is the contravariant tensor, right? While TMN is the covariant tensor. Yes, these two are different. Yes, they are different. And now, as I say, all of these, these two, they are contravariant tensors. Okay, while I can introduce also the covariant formalism. What is happening with let's say Tij. This is the covariant one. Covariant tensor of rank 2, for example. So Tij is given by AIK or AIM, AJN, TMN, which that was the short notation with the Einstein convention. So if you want to expand it, that will be the summation on M and N, and the first term will be derivative of X M X prime I derivative of Xn X prime J TMN, and that's a rank 2 covariant tensor of Ij. So you may build up a relationship between the two tensors, are covariant and contravariant, like transforming back and forth between the coordinates. Yes, this is why we have superscript. Yes, we have the superscript in exactly the same way. Yes, Mohammed. And Tij K is AIM, AJN, AKL, and you have TMNL. So you pay attention to the way that I'm writing this. So again, this is a summation over M, N, and L. And the derivative now is given by X power XM, X prime I, XN, X prime J, XNL, X prime K, T, M, N, and L. Lovely. So those are the covariant tensors of rank 3. So in general, you can write a tensor. In general, without writing the indexes, I mean, if you don't write the indices, the tensor, you can write it with a T double tilde, okay? Tilde. Usually I don't write it, but I see in the old school, people, they write it with a double tilde. Like, how did I write the vector? So the vector of R for me, vector I have written as R tilde. Okay, so, and here is a tensor. If you don't write the indices, you write it as a T double tilde. If you write it with indices, so you are defining the components of that, you can write T, I, J, K, L until, I don't know, Q. let's say P, just not get confused with the other one. And if those numbers, they are n indices, then we call these nth rank tensor. But which kind of tensor is that? Is contravariant tensor. Okay. If all of those indices, they are in subscript, KL until P, again, n indices, then I call it nth rank tensor covariant, indeed, tensor.
There are two questions, sir.
Yes, and let me explain the last one, and of course, the vision will come back to you. And now I can have a mix of the two. So what is happening if I have T, for example, I, J, K, L, M, N, until you will get P. So when the indices are mixed like that, indices, of course, again is nth rank tensor, but I have to call it is a mixed tensor. That's a third case. Yes, Vijan, I'm with you.
Amir Hussein has asked, I assume that all physical anisotropic characteristics in matters are represented by tensors, right?
No, that's not correct. For example, spinors, they cannot be, they are not tensors, they are not scalar, they are not vectors. Okay.
Omid Mehravan has asked, what is the derivative representation of A sub IJMN?
Derivative representation of AIJMN, I don't understand, because I use the AI as the, the cosines, right? So I'm not following, to be honest. Omid, can you elaborate further on that, please? Okay. So should I follow?
You can continue. If
Okay,
he
thank you
answers,
very
I will
much.
let you know.
Yeah, thank you, Vijan. So, well, those are the, if you have any questions about the tensors, can you tell me? So, if not, I have to follow the calculations. Okay.
No, there ain't any questions.
Okay. So I introduced the tensors in even n indices. N indices means that, well, look at the scalar. Scalar has no index, So for example, the scalar of T, and I call it rank 0 tensor. It's going back to the question that Amir Hussein asked. What about the vector? Vector has one index, which this index is given either like a vector that is acting like a coordinate, which is like Ti, or is acting like a Ti. It can be contravariant, or it can be covariant. I call it rank 1 tensor. I can go with something like a permittivity of material, which is epsilon, okay? I call it permittivity or elasticity, is up to you, whatever you want to call it. So elasticity, gosh. Oh, let's go with permittivity. Epsilon ij. or epsilon ij. It's a rank 2 tensor. Okay, again, covariant or contravariant. Or okay, so those are the definition that I have. But remember, don't forget the important concept that I have. I can go with even Tij k or whatever, which is the rank 3 tensor. What is happening? Remember that this definition is based on rotating the coordinates x1, x2, and x3. If I rotate the coordinate to x prime 3, x prime 1, and x prime 2, then the way that scalar is changing is like that, which is not changing at all. The way that the vector is changing is like that. The way that the tensor of rank n is changing is like that. So that is the definition that I have. So it should follow a specific rule. And what is this specific rule? Is given by that rule. Or it is given by this rule. Those are the definitions that I have for the tensors. I can define different vector space and I can go with a different definition as well and different metrics. So you will see towards the end of this lecture. So is there any question, Vishnan?
Yes, Sabra Mandal has asked, what are the differences of contravariants, covariant, and mixed tensors? Give physical description with examples. The mathematical definitions of them, I understand what you've told.
Yeah, I saying, Subra, wait until that I'm giving an example, okay? If you can wait, that will be wonderful.
There's another question from Noria. Earlier, when you introduced Einstein notation, you gave an example with something like this: A sub ijmn, A capital hat M, B capital hat N. I think if the students meant this when they asked about A sub ijmn.
Oh yeah, it can be anything. It can be anything that I introduced. That can be explicit in that example, which is I just give an example in order to understand if you got what I mean. I think that's the example that I had here. This one or that one. I just want to tell you, well, if you understand the Einstein convention rule of summation. So this was an example. What is the meaning of AIJKL? I'm now asking you. It can be anything, but can you tell me what is this form? What it should be the form of AIJKL? What's that? Can you type in Q&A? Now you have just learned this. Is it a vector? Is it a scalar? Is it a tensor? If it's a tensor, which rank is? No idea? Exactly. Is a force rank. No, it's a force rank because it has 4 indices, right? This specific example, that was contravariant tensor, and this one is the covariant tensor, okay? I can go with something very arbitrary right now. I mean, look at this one. I can write TIJLM, okay? And then I have another tensor of A, which has J and L. When I write these, using the Einstein convention, what does it mean? Is a summation over the J, right? And also is a summation over the L, right? then the result of these will be any new tensor which has a free I and free M. So I call it IM. Okay.
One has asked a question, sir.
Yeah. Yes, please.
Mohammed has asked, Professor, I think you said that in Cartesian coordinate, we don't have co/contravariant. Does it mean that we need them only in curved coordinates, or other coordinates can have it as well?
Well, other coordinates, they can have it as well. In the Cartesian coordinate, we have contravariant and the covariant formalism that they are identical. Okay.
And Amir Hussein has asked, so we should count the dummy indices too as the rank of the tensor?
Yes, if for example, if you look at these tensor of T, of course, the dummy index is important. So if you look at these the rank, the fourth rank tensor, which is a mixed tensor, by the way. Okay. What about the A? This is also rank 2 or second rank tensor, which is again mixed tensor. What about the result of these two, the product of these two, and doing the summation over dummy index? What you will get? You will get a tensor of rank 2. Okay, which is, by the way, contravariant tensor. So you have two mixed tensors, you sum over the dummy indices, and what you will get a rank 2 tensor of contravariant. Okay.
One has asked, can we have mixed vector?
Mixed vector. It has one index. How do you write a mixed vector? I have one example, which is pseudo-antisymmetric matrices, which I can build up some kind of vectors from it, but I will leave it to you. Summation of two tensors is always a tensor. We will see that. Yes, we will see that. Yes. Okay. If there is no question, please share the attendance. Okay. So if there is no question, I will go with how to handle the tensors. So far, this session, I mean, until now, which is almost 1 hour, I only introduced the tensors, the covariant formalism, and the contravariant formalism. And I told you how the conventions they are introduced and how we should handle the conventions. Now hereafter, what I will do, I will say something more. Isa is replying to the question that they say that, can we have a mixed vectors? And Isa say correctly that, well, has one index, and these index cannot be in both let's say in subscript and superscript at the same time. Isa, there is a little bit trick that I may be able to create that, but I have to use the pseudo tensors to build up that. So just wait. Okay. I'm not sure of that, but I think I can make a guess that we can build up something that can answer to the question that were asked previously. So I have a tensor of A and I have a tensor of B. How do I sum them up? A plus B. Can I sum them up? That's a question. I'm looking at the Q&A. Yay or nay? Yes. Mobin says yes. Surely, why not? Depending on the rank, Isa says correctly. So if that's a rank of n, that must be also the rank of n. Else you cannot sum them up. So assuming yes, if they have the same rank, they have the same rank, then the summation of these two will be given in the same fashion. So Aij, whatever, plus Bij, whatever, will be equal to Cij, whatever. Okay, that's important that you should notice. And well, can we subtract them? Yes, of course. Tensor of A is equal to tensor of C minus tensor of A. So again, sorry, my apologies. Tensor of B. Then in the same way, what is the result of these? Aij will be Cij minus Bij. And in the same way, can I do it for Aij k whatever plus Bij k whatever minus Cij k whatever? Yes, I can do that. And well, remember that what I have written the tensors in the same fashion. If they are contravariant or covariant or the mixed one, they should be identical. And this way that the different elements, you can sum them up together. You may ask, if I have a contravariant and a covariant one, can I sum them up together? Well, you can sum them up together, but you don't get a covariant and you don't get a contravariant. You will get something, a complicated situation between. Okay, so you have to be careful with that. Can you introduce a negative to a tensor? Yes, you can do a negative to a tensor. What you will do, you will just give them each element that you have each element of Aij that will becomes minus Aij. Okay, each element will get a negative sign. Okay, so that is about the summation, and we can do a little bit of calculation and also introducing some before going to the dots, which was also the question that one of the students they were asking. Before going there, let's go with a few examples. So I'm asking you, what is happening with the derivative of xi with respect to xj? Is there any question, by the way, Vijan?
Yes, sir. Mondel has asked, can we have a tensor like A capital sub II or B capital sub JJ?
Oh, I answered these. Yes. Well, if the question is about the if you write AII, I will discuss that. It will be essentially something like taking the trace. So it will be contractions indeed.
One has asked, is there dot and cross products of tensors, or what type of multiplication is between tensors? Is the result of multiplication of tensors always tensor?
I will be discussing in maybe 5-10 minutes.
There are two other questions. Mondel has asked, can A capital sub IJ and B capital sub MK be added? There are two and rank, both but different subscript.
Oh no, the subscript is just a notation that you use. Okay, is absolutely not important. So when I have written here, well, indeed, if we look at let's go before going here. So I have written A plus A, tensor of A plus tensor of B. Okay. So, well, when I write the index of Ij, okay, this means that, well, I'm looking at individual elements of this tensor. When I write BKL, again, is individual elements of B tensor. What are I, J, and K and L? They are indices. They are free indices. So, for example, the first one will be A11, right? In the 3-dimension, A12, A13, A21, A22, A23, A31, A32, A33. This is the tensor of A. But remember, it's not a matrix, okay? Why? Because A11 in a matrix, all of those elements, they are constant. Or they are not changing. They are not changing when someone changes or rotates the coordinate. Rotates the coordinate. However, if you rotate the coordinates, Aij in general, each of those elements, they will follow the cosine rule, which is Aim, Ajn, M and N. Okay. And the same situation is for B. So if you write B tensor is B11, B12, B13, and B21, B22, B33, sorry, 23, B31, B32, B33. So when you do A plus B tensor, this means that you sum them all up. So it will be A11 plus B11, A1. Sorry, guys. I was not careful with the placing the indices. That will be B11, B12, B13, B21, B22, B23, B31, B32, B33, and that will be B11, A11, B11, A12 plus B12, A13 plus B13, and the same, A21 plus B21. So this is what I mean, that these indices, because I'm looking for the result of C, the result of C, it should be the same indices that you sum them up together. So B22, A23 plus A2, oh gosh, I'm not concentrating very well, sorry. A23 plus B23, and A31 plus B31, A32, B32, A33 plus B33. So this is what we call it the C11. This is what I call it C112, C13, C31. So if you look at this expression, then Cij is equal to Aij plus Bij. So you are not allowed to sum one index there and another index there. So you have to go with elements, then sum them up together. Okay? Oh,
There are
matrices.
some more questions.
Yeah,
Shall I read them?
matrices is the plural of matrix. Okay, but what I say here is a tensor. Tensor is different from matrix, or tensors are different from matrices. Okay, why? The matrix elements or the matrices, upon rotation, they are the same. The elements, they are the same. If you have 1, 2, -5, 6, 7, whatever that you have it, if you change the coordinate, they are the same. But that's not true for tensors. That's the reason that refractive index is important. For example, refractive index, moment of inertia, the pressure, all of them, they are changing. If you rotate your head, if you write the pressures in those coordinates, will be different. Okay.
There are a few questions, sir. Shall I read them out?
Yeah, you can just go ahead. Yes, please.
One has asked how the sum of tensors would look like if the dummy index are different. For example, A capital had ABC plus B capital had DBC. Lowercase letters are indexes.
So, well, the dummy indices should be in opposite way. Okay, just to tell you. That's important. In your book, you have not defined that. It depends on the textbook, but in my notation, always it should be one up, one down. I'm not allowed to write it in this way.
Sabra has asked, when you write A capital had IJ, that is tensor component, right? Not the whole tensor.
No,
is
the component, yes. Is AIJ is the component of tensor A. Yeah.
And if you sum a matrix 2 cross 2 and a 3 cross 3 one, both have same rank. Rank is not only the crucial condition then.
Oh, well, you are missing a very important factor. So we assume that they are all of them, they are in the same space. We assume that I, J, K, whatever we have, is in the same space. So it means that if, for example, right now we consider that is a dimension 3 space, I have not considered dimension 2 space. Okay, of course. When tensor is equal to matrix? Never. Tensor is, as I say, is the elements that are changing, the components are changing according to the cosine rule. So this Aij is changing according to this, is changing as a x prime I, x j, xm, x prime j, x n, a m n. Okay. While the tensor, the matrices, if you have a matrix of Aij, this is equal to A prime Ij. This is for a matrix. And here is for a tensor. Upon rotation does not change one of them.
One has asked, can we say matrix is a specific type of tensor?
No, I wouldn't call it. It's a scalar quantity.
And can we say tensor and matrix are similar in the form but not in the content?
Yes, that is true.
Sometimes are not tensors represented in matrix forms. For example, metric tensor. What do they mean?
sometimes are not tensors represented in matrix forms. So, for example, epsilon ijk, right? Epsilon ijk is a pseudo tensor. You will see it today. How do you show it? In the matrix formalism. Epsilon Levichovitch notation, ik. So the index of I, J, and K for the three-dimensional space is going from 1 to 2 to 3. Okay. Now, can you show me the matrix? Yes, it is possible that the tensor has a 0 element. So if I'm asking you to show this, you are not able to show it with the matrix formalism. If you want to show you the matrix formalism, you have to write one matrix like this, another matrix like this, and another matrix like this. So the first one is when I is equal to 1, I is equal to 2, I is equal to 3. So if you show this, that is this arrow is J, and this arrow is 1 is K. So if it's 1, 2, 3, is 1, 1, that would be 0, 0, 0 always. Is 1, 2, and K is 1 again, that will be 0, that will be 0 as well. J3, K1 is 0, and when I is equal to 1, that also is 0. This part will be 1, 3, 2, that will be 1, 3, 2 will be -1, and that one will be +1. Let's see. Yes, it will be the inverse of this. And the other part will be the 2. 2 means that the line of 2 will be 0. So it will be 0 here, will be 0 here, will be 0 here. And 2, and that is again I, that is again K. 1, 1, that will be 0. 2, 1, 1 is 0, is 0. Sounds strange. 2, 1, 3. 2, 1, 3, 2, 1, 1. Okay. I think that is 2, 2, 2, 1. That will be 2. J is 3, K is 1. 2, 3, 1, that will be -1. -1. Definitely that one will be +1, and that will be 0, 0. And sorry, guys, it takes time because I have to do the calculation. That is J. For that one is a 3. So the 3, definitely J3 is equal to 0. K3 also is equal to 0. Then that will be 2, J1, 1, that was 0. 1, 2 also, 2, 2 is equal to 0. That one will be J2, 1, 3, 3, 3, 2, 1, that will be -1. And that will be +1. So you will see that these are matrix, these are a tensor, a pseudo tensor essentially. But if you look at the pseudo tensor of rank 3, you cannot show it with a tensor. If you want to show it with a tensor, essentially, it looks like having a cube, right? And this cube, has 3 elements. if you want to show it. Okay, and these are the three elements. The first one is here, the second one is here, the third one is here. Okay. Other questions?
Yes, Muhammad Abdul Aziz has asked, what about Kronecker delta? Is it pseudo tensor as well?
I did not introduce even the pseudo tensor, so I have to introduce the pseudos. I have not defined that yet.
All right, Muhammad Said has asked, is spin of particle tensors?
Well, as I say, that you have to be careful what you mean by yes and no, depends on the particle. If it's a 1/2 spin, no, it's not a tensor. Okay, if it's a spin 1 particle, then I will call it is a vector, is a rank 1 tensor. If it's 0, then that will be a scalar.
Another question is that as tensor is not a matrix, then how do we multiply two tensors written in matrix form?
I have not even defined the product of the two.
Shaho M. Rasul has asked, isn't it 231 equal plus 1?
So do 231, 231. Let's go with the notations. Maybe I have done a mistake. So is 1, 2, and 3, and 1, that is equal to plus 1. So 3, I start from 3, okay, based on your 2. I will go to 3, I will go to 1, and is a plus 1. Yes, that is correct. So where I did say that is 2, 3, and 1. Yes, that is a plus 1, and the other side is minus 1. Thank you very much.
There are no more questions, sir.
Oh, fantastic. So I hope that you at least you get familiar with the notations of the tensor. And again, I'm repeating myself. Tensors, they change based on the rotation that you do. Okay, it's very important to pay attention to that one. So now let's look at the few examples that previously we just treated them as a scalar. Okay. What is happening with the derivative of xi with respect to xj? In a short, people, they write it jxi. Pay attention. What is I and j? They are indices, right? So they can change from 1 to 3. So you can take the derivative of x with x1 with respect to x2, or x1 with respect to x3, x1 with respect to x1. What is the result? Can you write in the Q&A? Kronecker delta. Lovely. I will write it as a delta, but now pay attention to where the indices are located. So I is superscript. What about xj is in the denominator? I will write it as a j. So if you forget, just pay attention to the short notation. Is the derivative with respect to j of xi. So it seems that delta ij, what's that? Is it a scalar? Is it a tensor? If it's a tensor, which kind of tensor it is? Can you type in the Q&A? I'm looking at the YouTube channel just to see if there are questions there. No, only Mr. Hussein Rabi is kindly paying attention. Okay, so well, some people they say is a coefficient. Other people they say is a mixed tensor, is a rank 2 tensor. Nuria say the same. Subra mixed tensor, Amir Hussein mixed tensor. Lovely. First of all, is a mixed tensor. What does it mean? That index of I is going as a contravariant, and index of j is going as a covariant formalism. And on the other side, what I see that is a tensor of rank 2, is a tensor of rank 2. Good, but it's a mixed tensor. Lovely, fantastic. You get it very well. And what is the result of these guys? When I is equal to j, that is equal to 1, else is 0. If you want to show the matrix representation of that, that will be 1, 1, 1, and the rest will be 0. But it is a tensor, remember. Okay? Let's prove that these tensor, let's look at the tensor. Look at these tensor upon rotation in space, or rotation of coordinates. If it's a tensor, then it should follow the notation that we have. So indeed, a delta of ij prime, I want to find it out, the result of these in upon rotation, that will be aik or m a jn delta of m n. Okay, do you agree? If this is a tensor, then in the rotated coordinates, that will be the result. Okay, this is the definition. I don't care about prime now at this stage. Okay, at this stage, I don't care about that. What is the result of this? We know that the delta of m and n, when m is not equal to n, is 0. When m is equal to n, that will be a 1. So what we do usually, we replace one of the m with n values, and we take away the summation. So that will be ain, anj. Do you agree? The summation is over what now? The summation is over the repeated indices, which is or dummy index of n. Do you agree, or do you have a problem with that? Do you remember that we had the summation of, let's say, any function of f, m, n, and then we have a delta of n, m, n? Then we say that the summation will be gone, and you replace it with f, n, n. Okay? And now we have two indices of n, and then the result of these will be n. And now let's do the mathematics. What is in? Is a derivative of x prime I with respect to xn. What is this one? Is derivative of xn with respect to x prime j. Remember, I'm not writing, but remember that always there is a summation here, which is the summation over the n, which is the dummy index. Okay. Then the result of this will be summation. I don't write it usually, but I'm writing for simplicity here, is the derivative of x prime of I, derivative of xn, derivative of xn, derivative of x prime j. What is the result of this, guys? It reminds you of something. Is a chain rule, right? Is derivative of x prime I, derivative of x prime j. which is again delta of ij. Okay, so it seems that these delta of ij, which I have written in the matrix notation here for you, and I have expanded the components. If you do a rotation, is the same. You may have some kind of tensors that they have this property, and we call these kind of tensors isotropic tensor. And in this example is isotropic tensor of rank 2, which is a mixed tensor, by the way. Okay. Questions?
There is a question from Shaho and
Yes.
Rasul. In Delta Chronicle, we have no in dollar signs, x prime slash prime, x hat slash prime. So can we say that we have no rotation of coordinate system?
Oh, we have just done the rotation. I just showed that what is happening when you do the rotation.
There are no more questions, sir.
Yeah, okay. If I didn't answer to the question, please type it. Okay. In the upper left, okay. Partial xi, partial xj is a delta of delta ji. Oh, you can write it in this way. Yes, doesn't matter. I mean, for me, it's not important. Yes, Shao, you can write it in this way. There is a prime, there is prime where I don't see the prime. The prime appears only here. And I'm looking at this one. I say that what is happening upon the rotation, and that was the question. I say that what is happening with the delta prime ij, what is happening with the component of the delta ij upon rotation. Yes, we call Amir Hossein, yes, we call it isotropic. Yeah. Perfect. Now, tensors, they have some nice property. So, and those nice properties are given in this formalism. I mean, if we assume that I have a tensor of T, let's say ij, let's go with the rank 2 tensor. Then this tensor, well, has certain components, as we discussed. It can be written as a T11, T12, T13, T21, T22, T23, T31, T33, and well, that's the tensor of T. The components that I have expanded in this formalism. Now the question is that what is going on with the property of that? Well, it all depends on the property of the tensor. But what I can do, I can take the tensor of T and I can write it as a 1/2 of Tij plus 1/2 of the Tij. And then I can add Tji. I will swap the indices, and I can subtract also the Tji. Result of this is 0, by the way. What I will do, I will just add it and subtract it, this value, and then I will cast it in this way. Then it will be 1/2 of Tij plus Tji plus 1/2 of Tij minus Tji. What I have done, I have taken these parts and I will add it to this, and I have taken these parts and I will add it to that part. So now I have two parts of the tensor. I will call these the symmetric part, and I will call these one the anti-symmetric part. What does it mean? if you take Tij, the symmetric part, plus Tji, 1/2. The coefficient is not important, by the way, in that stage for me. If I change I to j and vice versa, then what I will get Tji plus Tij, which is identical to what I had previously. In the antisymmetric case, I have Tij minus Tji. If I swap I and j, then what I will get? I will get minus Tij minus Tji, which is negative of the case. So well, it seems that this tensor that I had, I can write it in two parts. Let's write it the two parts. The first part is 1/2 of Ti, as I say, that it will be Tij plus Tji. It will be 2T11, and the second term will be T11. Sorry, my bad. T12 plus T21, T13 plus T31. And you can do the calculation, the rest, T21 plus T12, 2T22, 2T33, and that term will be T3 plus T32, T31 plus T13, and T32 plus T23. That's the first part, which is the symmetric way, and the antisymmetric way will be 1/2 of T11 minus T11, which is 0. And the other term will be T12 minus T21. And this term will be T12 minus T21. This will be 0. That will be T13 minus T31. T23 minus T32. I stop because I want to understand where should I place the sign. That will be minus T13 minus T31, and finally that will be minus T23 minus T32 and 0. So that is the antisymmetric, and that's a symmetric tensor, which is important also in our calculations. I mean, that you will see in future. Questions so far? No questions.
No, sir.
Lovely. So that is the way that people we can build up the symmetric and antisymmetric way. Now I will go with the definition that they were asking also during the lecture, which was about the dot product, which I call it indeed contractions. So you can take a vector of A, which was A1, x1, a2, x2, plus a3, x3, and then you can take another vector of B, which was b1, x1, b2, x2, and B3 X3. And you can introduce A dot B, assuming that X1, X2, and X3, they are mutually orthogonal to each other and they form a right angle, not necessarily a right angle, but anyway, what you will get A1, B1, A2, B2, and A3, B3. And indeed, that I can write it as AI, BI. Well, remember, I have not paid attention to being covariant and or contravariant. This is exactly the example that we had it from the Cartesian coordinate, or even curvilinear coordinate, which I say that you can take the dot product and you can get the following expression, okay? Now, let's introduce something like that. What is happening? Is this a vector? Are they vectors, T2? I'm introducing an operator, dot operator, which what does it do? It takes the two vectors of A and B and bringing them to being a scalar quantity here. So it seems that it lowers the dimensionality, or it lowers the rank of the tensor and lowers it by essentially by a factor of 2. So by 2 orders. So it brings it down by 2 level. So you have a vector of A and a vector of B, and if you do the dot product from the 2 vectors, you will get a scalar quantity. And usually, when I was a lecturer at the university, some people, they called me Dr. Ibrahim, and I say, well, don't call me Dr. Ibrahim, because usually you write it as a Dr. dot Ibrahim, and I make a joke, by the way. I made a joke at that time, and I say that, well, Ibrahim is a vector quantity. Doctor can be a vector quantity, and that you have a dot product, and the result is a scalar. Okay, so just to remember, the dot product brings the rank of the tensor by 2 orders lower. Okay, by 2 values, and you will see what do I mean by this. Let's erase this. So, assuming that I have a tensor of Tij, and I want to reduce the space, okay? Well, I want to reduce the space, reduce it down. So what I can do, I have to do the summation over the indices. Okay, so what I have to build up from this, I have to build up Tii or Tii, one of these two. And if I built up this, I contracted a scalar quantity from this tensor, which essentially, if you look at the matrix formalism, in the matrix formalism, that will be what we call it, the trace of the matrix. But remember, it's different because the trace is a constant, and here we are dealing with the matrices are constant. Here we are dealing with a tensor. Okay. So let's go with an example. I want to do the calculation of Tii, and I want to show that this is a scalar quantity. You can build up that, by the way, with the delta functions if you work with. So if you have a Tij, if you multiply it by delta of Ji, then the result of these will be Tii. Okay? Do you agree on that? This is the way that I will build up the contractions. So I will multiply the elements by the delta functions in this fashion, and I will get the results that I wanted. So assuming that I want to look at the TII, so I'm not going to, I mean, these, I just want to tell you that, well, we can get some expression like that. So what I want to do is that, well, this is the second rank matrix of the mixed tensor. Sorry, I used the matrix, the second rank mixed tensor. And what I want to do, I want to show that this is invariant. What does it mean? If I have a TI, which I do the contractions, then I have to show that this is the same in the rotated coordinate. So I have to calculate what is happening with in the rotated coordinate of T, let's say either you call it II or Tij. So let's do the calculation. If that's a mixed tensor of II, then definitely they should follow the tensor formalism, the rank 2 tensor formalism. So indeed, T prime Jj, that is equal to derivative of x prime I with respect to xi, and then I have the derivative of xj, and then I have x prime I of the tensor. Okay, let's go with a very general formalism. Let's go with N and M and T, N and M. Okay. And remember again, the summation is over N. The summation is over M as well. So this is what I'm dealing right now with it. And I want to do the calculation and find out what is happening when when I'm setting, we are looking at T and M. So indeed, I will replace N with M. So I will get the derivative of x prime J, derivative of xn, derivative of xn, derivative of x prime J. Sorry, my apologies. You don't need that. Using the chain rule, indeed, that becomes derivative of xm, derivative of xn, of tn and m, and that is nothing more than delta of m and n of t and m, which the result of this will be t n n, which we are showing that in rotated coordinate, the t prime j is identical to t and n of not rotated coordinate. Rotated is equal to non-rotated one. Remember that is t11 plus t22 plus t prime 33, which is equal to t11 plus t22 plus t33. Okay, so that is what we obtained. So in not rotated, we just show that essentially someone can can build up a scalar quantity from a tensor of rank 2. So you reduce the rank by 2 orders. Well, the same way we can apply also, and we can create a tensor from a vector. For example, you can take a vector of AI, which is a contravariant vector, and vector of BI, and well, let's call it BJ just to make it distinguish the indices. They are different because that is the component that essentially you have is A1, A2, and A3. And then this one is a B1, B2, and B3. And remember that those are the contravariant vectors. And you can have the same one, AI, which is covariant A1, A2, and A3. I can have also BJ, which is B1, B2, and B3, which they are the covariant vectors. And now I can start to use them and building up a tensor from this. So they are the first rank tensors, and I'm building up a rank 2 tensor from them. How can I do that? So essentially, A, if is a vector, essentially is given by Aij, Aj, and B the same one. If is a vector, B prime I is equal to Aij, Bj. Now, what I will do, I will build up what is happening with A prime I, B prime K. What is happening with these two together? If you multiply it, then it will be Aij, Aj. That's a summation over the J, and then B prime K will be AKL, BL. And if you cast them together, it will be Aij, AKL, Aj, BL. So I can call these elements of the tensor, because these two are the cosine rule for tensor of rank 2. And that one, indeed, if we look at them, I can call it TJL. So if you take the two vectors, if you multiply the elements together in this way, T of JL equal to AJBL, or you can write it in a simple way because I used different indices. So you can write it TMN equal to AMBN, then you are building up a tensor of rank 2, second rank tensor. And indeed, if you want to expand it, this T tensor in terms of the matrix notation, that will be A1, B1, A1, B2, A1, B3, A2, B1, A2, B2, A3, sorry, A2, B3, A3, B1, A3, B2, and A3, B3. This is what we call it direct product, which brings up the tensors rank by one order of magnitude. You take the two vectors and you do the tensor product and you will bring it up. So as an example, I can tell you, I will be done in 1 minute. So if you remember, the gradient is a vector. If you remember, right? And the vector was a covariant vector because the element was given by derivative with respect to x1, derivative with respect to x2, derivative with respect to x3. Or in short notation, people, they write it derivative with respect to I. And then, for example, vector of electric field is a vector, is a contravariant vector. And I write it with E1, E2, and E3. Or in short, I will write it EJ. So gradient of a vector that previously we have not introduced, it was one of the questions that you had, now is a tensor, is a rank 2 tensor. And in short, we write it, the elements, we write it as I, E, J. That's a tensor of I, J. How that is evolving upon rotation, changes upon rotation, coordinates rotation, is given by Tij. Let me write it in this way. Derivative prime of Ej prime. That will be AIM BJN, derivative of MEN. Okay, and that's the way that is changing upon the rotation. So I will stop here and I will stop the videos, and I will wait for the questions. Thank you very much.